Fishes to swim through viscous, dense water, and salt is even more dense than fresh water, have to push themselves through molecules that are very dense and viscous. Therefore, there's a lot of friction drag.
You want to think of it as the stickiness of seawater. It's really thickness in a sense. I think the best way to understand viscosity is to think about how much easier it is to run on land than it is to try to run through water.
There's a lot of frictional components there that an animal that lives in air doesn't face. Just try running your hand through your bathtub water and then lift your hand up and run it through the air. It takes more energy to get through the water, and most fishes, they face this problem every single second of their lives. How are they going to get through the water through this very viscous medium?
For very big things that move very fast, viscosity almost disappears. For very small organisms, viscosity is the dominant force. It is the biggest thing that constrains everything they do. Because when you're living in a bath of molasses or honey, how do you find food? How do you get from one place to another? It becomes very difficult to move. It becomes very difficult to do anything.
Difficult, but not impossible, thanks to a host of adaptations that enable marine organisms to function in this challenging environment.
Fishes, in particular fast fishes, some of which can travel up to 70 miles per hour in the ocean, the very fast tunas and marlins and those types of fishes, they have adaptations really to streamline their bodies and to try to reduce viscous forces on their bodies so that they can swim more rapidly through the medium.
So how are they going to do that without expending huge amounts of energy? Because really in evolution, that's the key. How do you do what you want to do expending the least amount of energy? And there's huge selective pressure to do that, to be as efficient as possible. So how do fishes do things most efficiently dealing with this very difficult medium? Well, the first thing is, for those fishes that have to move a lot, you can reduce the amount of friction on your body. You can cut down the size of your scales. Scales stick out and produce a lot of friction. There are fishes that have no scales. They've taken it all the way down there. You can have your fins, which stick out and produce friction, tucked down into little folds. If you look at a tuna, when it's swimming fast, the fins on its sides, the pectoral fins, fit really neatly into little grooves so that it's smooth along the sides of its body. So you can reduce friction that way. You can produce mucus. Most fishes do that, which also reduces viscosity between your body and the water. So that's certainly a way of being able to move through the water in a more efficient way.
Another element that adds one more challenge to the mix of conditions that fishes must face is turbulence.
Turbulent environments are the kind that you might encounter in coastal regions where you have breaking waves, or if you're living on a rocky shore with waves breaking, it would be very highly turbulent. This turbulence would tend to want to rip you off the rock if you were an animal living on the shore. And some of these animals living on rocky shores in particular, again, have adaptations that help dispel those forces and help prevent them from being ripped off the rock, whether it's having a very strong glue, like in the case of barnacles that are literally just one of the strongest glues in the world that glue them to the rocks, or having sort of a kind of amorphous body that can kind of move with that turbulence as well.
One of the factors that in part determines the amount of turbulence at a given location is depth.
The deeper you go in the oceanic water column, the more the environment becomes calm. Up near the surface, it can be very active. Wind-driven circulation and things like that make a very challenging environment for an animal to hold position or to move through. But as you go deeper, things calm down. And in very deep water, below 1,000 meters, there is very little water to struggle against.
Light, temperature, pressure, salinity, viscosity, turbulence. Each of these plays a part in defining the oceanic environment. And it is against this diverse backdrop of challenging and dynamic elements that the animals of the world's ocean wage a daily battle for survival. Scientists who attempt to categorize or classify the different areas within the marine environment face a challenge of their own which, while certainly not a matter of life or death, is nonetheless considerable.
Classifying the marine environment, there are multiple ways of doing it. There has never been, at least to my knowledge, a universally acceptable classification of the marine environment. You could say, well, you can classify the marine environment into those things that live in the water column and those things that live on the bottom. That's one way, pelagic and benthic. You could also classify them by depth. Those that live on the surface, those that live in midwater, those that live in deeper water, just going down and going through layers of water. And in fact, that has been done, and people talk about the various depth zones. Someone will say, well, I work in the mesopelagic. Well, what does that mean? Well, that means that you work in a midwater area that's between 700 and 1,000 meters deep, let's say, something like that. So you could classify them that way. You could classify the marine environment like you classify the terrestrial environment. You could say, well, we could talk about polar marine environments, we could talk about temperate marine environments, we could talk about tropical marine environments. So there's all these different ways of doing it. And each one has a certain validity depending on what you're trying to get across.
As difficult as it may be to categorize the various realms of the marine environment, it is perhaps even more daunting to classify the 25 to 30,000 species of fishes that live in that environment.
One of the things we really want to do, besides trying to find out as much as we can about the ocean environment, is part of that is learning what's in the ocean. And we can't really understand or even begin to comprehend the ecosystem unless we know who the players are.
Life in the ocean is classified really in the same way as we classify all life. We break life into categories that make it easier for us to understand the relationships between organisms, not only the relationships in terms of whether they get along or don't get along, whether one's eating the other or not, but also sort of their evolutionary relationships.
Organizing animal life by phyla is perhaps the most commonly practiced form of classification.
There are currently approximately 35 different animal phyla on Earth. I'll give you an example of a phylum. The phylum Arthropoda, the arthropods. This would include insects, it would include crabs, lobsters. That's an example of a grouping. Echinoderms, the sea urchins, the sea stars, would be an example of another phyla.
The simplest organisms that we find in the ocean are probably the sponges. Very simple organisms, but they seem to be the first ones that arose, the first multicellular organisms that arose in the oceans.